Hello everyone, I'm Prutha and this is my partner Karthik. Today, we're going to take you through an interesting and important topic in signal processing. Our goal today is not just to explain the theory, but to help you build an initiative understanding of how this concept is applied in real world scenarios. Let me start with a simple question. Have you ever listened to a song and thought about what's actually happening behind the scenes? It feels like one smooth piece of music, right? But in reality, it's made up of many different sounds, instruments, and frequencies all combined together. Now, imagine this. What if we could take that complex sound and break it down into its individual components? What if we could see the hidden structure inside a signal? That's exactly what today's topic is about, decoding waves using Fourier analysis. In simple words, we're going to learn how complex signals can be understood as combinations of simple waves. To understand this, let's go back in time. In the early 1800s, a French mathematician named Joseph Fourier was studying how heat flows through solid objects. While working on this problem, he came up with a very bold idea. He said that any periodic function, no matter how complicated, can be expressed as a sum of simple sine and cosine waves. At that time, this idea was quite shocking. Many scientists and mathematicians did not agree with him. They believed that irregular or discontinuous functions could not be represented using smooth sine waves. But Fourier persisted. Over time, his theory was tested, verified, and eventually accepted. And today, what started as a study of heat flow has become one of the most powerful tools in science and engineering. It's fascinating how a single idea can evolve into something so impactful. So, now that we've understood where this idea came from, let's move into the heart of today's topic, what Fourier analysis actually means and how it helps us decode waves. When we say decoding waves, what are we really trying to do? In simple terms, we're trying to understand what a complicated signal is made up of. Most signals that we encounter in real life are not simple or clean. They don't look like perfect sine waves. Instead, they appear irregular, complex, and sometimes even random. Now, here comes the powerful idea behind Fourier analysis. It tells us that no matter how complicated a signal looks, it can always be broken down into a combination of simple sine and cosine waves. At first, this might sound surprising. How can something so irregular be made up of such smooth and simple waves? To understand this better, let's think about sound. Imagine you're listening to a musical chord played on a piano. When you hear it, it feels like a single sound. But in reality, that chord is made up of multiple notes being played at the same time. Each of those notes has its own frequency. Your ears hear the combination, but they don't separate the individual notes. Fourier analysis does exactly that. It acts like a tool that can take that complex sound and separate it into its individual frequency components. It tells us what frequencies are present and how strong each one is. Let's take another simple example. Think about a smoothie. When you look at it, it appears as a single uniform mixture. You don't directly see the bananas, the strawberries, or the milk inside it. But if someone analyzed it carefully and told you exactly what ingredients are present and in what quantity, you would get a much clearer understanding what that smoothie actually contains. In the same way, a signal might look like one complicated waveform, but Fourier analysis reveals the ingredients inside it, the different sine and cosine waves that make it up. Now, you might be wondering why sine and cosine waves specifically. The reason is that these waves are the most basic forms of oscillation. They're smooth, continuous, and repeat in a predictable pattern. Because of these properties, they serve as ideal building blocks for constructing more complex signals. In fact, you can think of sine and cosine waves as the alphabet of signals. Just like we use letters to form words and sentences, we use these basic waves to form complex signals. Now, let's take this idea a step further. Whenever we look at a signal, we usually observe it in what is called the time domain. That means we're looking at how the signal changes over time. For example, we might plot a graph where the horizontal axis represents time and the vertical axis represents amplitude. This view is useful, but it doesn't always tell us everything we need to know. Sometimes we're more interested in understanding what frequencies are present in the signal rather than how it changes over time. And this brings us to another important concept, the frequency domain. In the frequency domain, instead of looking at time, we look at frequency. We ask questions like what frequencies exist in this signal and how strong are they? Fourier analysis is the tool that allows us to move from the time domain to the frequency domain. It transforms the signal into a completely different representation, one that often makes hidden patterns much easier to see. You can think of this transformation as changing your perspective. It's similar to looking at a building. From the outside, you see its shape and structure. But if you look at its blueprint or floor plan, you understand how it is organized internally. Both views describe the same building, but in different ways. In the same way, the time domain and frequency domain are two different ways of looking at the same signal. Another important idea here is the concept of superposition. This means that multiple simple waves can be added together to form a complex wave. And interestingly, the reverse is also true. A complex wave can be broken down into those simpler components. Each of these simple waves has certain characteristics. It has a frequency, which tells us how fast it oscillates, and amplitude, which tells us how strong it is, and also has a phase, which tells us its position or shift. By combining many such waves with different frequencies, amplitudes, and phases, we can reconstruct the original complex signal. And this is what makes Fourier analysis so powerful. It doesn't just break signals into parts, it gives us a structured and meaningful way to understand them. Now, you might ask, why do we go through all this effort? Why not just work with the original signal as it is? The answer is that many problems become much easier when we look at signals in terms of their frequencies. For example, if a signal contains noise, we can remove unwanted frequencies to clean it. If we want to compress data, we can keep only the most important frequency components and discard the rest. If we want to analyze a system, it is often much simpler to do so in the frequency domain. So, Fourier analysis is not just about breaking signals, it's about making them easier to study, understand, and manipulate. To put it all together, Fourier analysis allows us to take something that looks complicated and transform it into something simple and structured. It helps us move from confusion to clarity, and that is why it is such a fundamental tool in understanding waves and signals. Now, let's briefly connect this idea to mathematics. At its core, Fourier analysis is built on several important mathematical concepts. First comes trigonometry. Sine and cosine functions are naturally oscillatory, which makes them perfect for representing waves. Secondly, calculus. We use integration to calculate how much of each frequency is present in a signal. Next, linear algebra. You can think of signals as vectors and sine and cosine functions as basis vectors. So, Fourier analysis is like expressing a vector in terms of its components. And finally, complex numbers. They help simplify calculations and make the representation more compact and elegant. So, even though the idea seems simple, it is deeply connected to multiple areas of mathematics. That's what makes Fourier analysis both powerful and beautiful. Over to Karthik.
Hello everyone, and my name is Karthik, and let's continue from here to the concepts of Fourier analysis. Now that we have understood the basic idea of Fourier analysis and why it is so important, let's take the next step. So far, we've been talking about Fourier analysis as if it is a single concept, but in reality, it is not just one method, it is a whole family of techniques. Different types of signals require different approaches, and over time, several variations of Fourier analysis have been developed to handle these different situations. So, in this part of the lecture, we are going to explore the major variation of Fourier analysis and understand when and why each one is used. Let's start with the most fundamental one. Let us begin with the Fourier series. When we talk about the Fourier series, we are dealing with signals that repeat over time. These are called periodic signals. If you think about something like an alternating current signal in electrical systems, it keeps repeating in a regular pattern. Similarly, many waveforms in electronics repeat after a fixed interval. The Fourier series tells us that any such repeating signals can be expressed as a sum of sine and cosine waves with different frequencies and amplitude. Now instead of focusing on the mathematical form, let's understand what this really means. It means that even if a single signal looks very complicated, as long as it repeats, it is actually built from simple waves. These simple waves are called harmonics, and each harmonic correspond to a multiple of base frequency. To visualize this, imagine trying to receive a square wave. At first, it looks nothing like a sine wave, but if you start adding sine waves of different frequencies in the right proportions, you will slowly see that the shape begins to resemble a square wave more and more closely. As you add more components, the approximation becomes better. This shows us that complexity can emerge from simplicity. A waveform that looks sharp and discontinuous can exactly be represented using smooth sinusoidal components. This idea is extremely useful in analyzing circuits, signals, and vibrations. However, there is one important limitation here. The Fourier series only works for signals that repeat forever. In reality, many signals do not behave like this. For example, uh, take example of you clapping your hands. The sound exact only for a short duration. It does not repeat periodically. Similarly, a spoken word or a pulse signal is not periodic. So the question becomes, how do we analyze signals that do not repeat itself? To answer that, We move to the Fourier transform. The Fourier transform is essentially an extension of the Fourier series designated to handle signals that are not periodic. Instead of focusing a signal to repeat, we allow it to exist as it is, even it even if it is occurs only once. Conceptually, what changes here is that instead of having discrete frequencies, we now deal with continuous range of frequencies. This means the signal can contain infinitely many frequency components. What the Fourier transform does is it tells us how much of each frequency is present in the signal. It converts the signal from the time domain into the frequency domain, gives us a completely different way of looking at it. To understand this better, imagine recording a musical note played on a guitar. The sound may seem like a single note, but in reality, it contains a fundamental frequency along with several overtones. The Fourier transforms can break that sound into its individual frequency components and show us their strengths. This is extremely useful in many applications, such as filtering noises from signals, analyzing communication signals, and even in medical imaging techniques. However, there is still a practical issue. The Fourier transforms assume that the signal is continuous and extend infinitely in time. But in real world systems, especially digital systems, signals are neither continuous nor infinite. Instead, they are sampled and stored as discrete values, and they exist only for a finite duration. So, we need another variation that works with digital data. This brings us to the discrete Fourier transform or DFT. The DFT is specially designed for signals that are discrete and finite. Instead of dealing with continuous function, we now work with a sequence of numbers. What this means is that we take a finite number of samples of a signal and transform them into a finite number of frequency components. This makes the DFT extremely practical for computers. Wherever you record audio, capture an image, or process digital signals, the data is stored as discrete values. The DFT allows us to analyze this data in the frequency domain. For example, when you apply filters to a photo or compress an audio file, the underlying components often involve transforming the data into the frequency domain using the DFT. However, there is a drawback. The DFT requires a large number of calculations, especially when the number of samples is large. This can make it slow, inefficient for real time applications. To overcome this limitation, we use a more efficient method. This is where the fast Fourier transform or FFT comes into play. The FFT is not a different transform, it is simply a faster way of computing the DFT. It uses clever mathematical techniques to reduce the number of calculations required. Instead of calculating everything directly, it breaks the problem into smaller parts and reuses immediate results. This significantly reduces the computational efforts. In simple terms, if the DFT is like solving a problem step by step without shortcuts, the FFT is like recognizing patterns and using shortcuts to reach the answer much faster. This improvement is very important because modern applications require real time processing, whether it is streaming music, processing images, or analyzing signals in communication systems. Speed is crucial. Because of the FFT, operations that would require otherwise take a long time can now be transformed almost instantly. Now, up to this point, all the methods that we discussed assume that the signal does not change over time. But in reality, most signals are not constant. For example, when let's suppose I am speaking, the frequency content of the speech changes continuously. Different words and sounds have different frequency patterns. If we apply a regular Fourier transform, we only get an overall frequency representation. We lose information about when those frequencies occurs. To address this, we use the short time Fourier transform. The short time Fourier transform or STFT allows us to analyze signals whose frequency content changes over time. This idea here is to take a small portion of the signal using a window function and apply the Fourier transform to that portion. Then we move the window along the signal and repeat the process. This way, we can observe how the frequency content evolves over time. This gives us a time frequency representation, which is very useful in applications like speech processing and music analysis. However, there's a limitation here as well. The window size is fixed, which means we have to compromise between time resolution and frequency resolution. A small window gives good time resolution but a poor frequency resolution, while a large window gives good frequency resolution but poor time resolution. This limitation leads us to the final and the most advanced technique as of now, the wavelet transform. It is designed to overcome the limitation of the STFT by using the variable size windows. Instead of using single fixed window, it adapts the window size depending on the frequency. For high frequency components, it uses small windows to capture rapid changes. For low frequency components, it uses large windows to capture slow variations more accurately. This adaptability makes the wavelet transforms much more powerful for analyzing real world signals. Another important difference is that instead of using sine and cosine waves, the wavelet transform uses wavelets, which are small wave like functions that are localized in both time and frequency. Because of this, it provides better resolution and especially because of analyzing signals with sudden changes such as edges in images or spikes in signals. It is widely used in image compressing, medical signal analysis, and many other advanced applications. Now, I would like Rutha to continue from here to the applications of Fourier analysis.
Okay, guys. Now we'll see what are the applications of a Fourier series. A Fourier series has many applications in mathematical analysis as it is defined as the sum of multiple sines and cosines. Thus, it can be easily differentiated and integrated, which usually analyzes the functions such as saw waves, which are periodic signals in experimentation. It also provides an analytical approach to solve the discontinuity problem. In calculus, this helps in solving complex differential calculations. Talking about the real world applications, they are widely applied in engineering, physics, and signal processing to analyze signals, solve differential equations, and compress data like JPEG images and MP3 files. Some of the key applications of Fourier series are signal processing and analysis. This is used to analyze the frequency spectrum of signals, filter noise from audio or communication data, and perform modulation and demodulation. Image processing and compression. Integral to algorithms like JPEG compression, feature extraction, and image reconstruction in medical imaging, such as CT scans and MRI, are furthermore applications. Vibration and structural analysis. This is essential in mechanical engineering for analyzing vibrations, identifying natural frequencies, and ensuring structures do not resonate, preventing potential failure. Next, solving differential equations. It is used to solve linear, ordinary, and partial differential equations like heat and wave equations by converting them into manageable algebraic equations. Electrical engineering. It is used in power systems to analyze harmonic content in alternating current circuits and in designing circuits. It is also used in data compression and signal modeling, where it enables the approximation of complex periodic functions using fewer data points, reducing the memory needed to store signals or images. So now, let's deep down on these applications, starting with partial differential equation. Fourier analysis provides a systematic and highly effective way to solve partial differential equations or PDEs by transforming them from the spatial domain into the frequency domain, where differentiation becomes much simpler to handle. Consider a typical PDE such as the heat equation, where the rate of change of a function with respect to time is related to its second order partial derivative with respect to space, or the wave equation, where second order derivatives appear in both time and space. These equations are often difficult to solve directly because they involve multiple variables and partial derivatives interacting simultaneously. Fourier analysis simplifies this by applying the Fourier transform with respect to the spatial variable, which decomposes the function into its frequency components. In this transformed domain, the fundamental operations of partial differentiation are converted into algebraic operations using key Fourier properties. A first order spatial derivative becomes multiplication by a frequency term, and a second order spatial derivative becomes multiplication by the square of that term with a negative sign. This means that expressions like del u by del x and del square u by del x square, which are differential operators in the spatial domain, are replaced by simple multiplicative factors acting on the transformed function. As a result of this transformation, the original PDE, such as heat equation or wave equation, is converted into an ordinary differential equation in terms of time for each frequency component. This is a major simplification because instead of solving a function that depends on both space and time, we now solve a set of independent equations that depend only on time, one for each frequency. Each of these equations describe how a particular frequency mode evolves. For instance, in the heat equation, higher frequency components decay faster over time due to the presence of second order spatial derivative, explaining the smoothing effect observed in diffusion processes. In the wave equation, each frequency component oscillates independently, which explains how complex waveforms can be understood as superpositions of simple harmonic waves. Once the transformed ODE is solved for each frequency, the complete solution in the frequency domain is obtained. The final step is to apply the inverse Fourier transform, which reconstructs the solution in the original spatial domain by combining all the frequency components. This process effectively reverses the decomposition and yields the physical solution. Throughout this method, important Fourier properties such as linearity allow multiple terms in the PDE to be handled independently, while the derivative rule directly links partial differentiation to algebraic multiplication, greatly simplifying the problem. Additionally, the convolution property becomes useful when dealing with non-homogeneous PDEs, where external forcing terms are present, allowing solutions to be expressed in terms of convolution integrals. For boundary value problems defined over finite intervals, Fourier series are often used instead of the continuous Fourier transform. In such cases, the solution is expressed as the sum of sine and cosine functions that satisfy the boundary conditions, effectively discretizing the frequency domain. This approach is particularly useful in solving equations like the Laplace equation for steady-state systems, where spatial derivatives in multiple directions are involved. Overall, by transforming partial derivatives into algebraic operations, decomposing complex functions into independent frequency modes, and reconstructing the solution through inverse transformation, Fourier analysis not only simplifies the mathematical process of solving PDEs, but also provides deep insight into how different spatial frequencies influence the behavior of physical systems. Coming to the second application, combinatorics. Combinatorics is a branch of mathematics concerned with counting, arranging, constructing, and optimizing discrete structures, particularly within finite systems. It studies how elements can be combined under given constraints and how such structures behave. While traditionally focused on enumeration and discrete configurations, modern combinatorics often interacts with Fourier analysis, especially through techniques like harmonic analysis on discrete structures, generating functions, and spectral methods. Fourier analysis helps translate combinatorial problems into the frequency domain, where patterns, symmetries, and structural properties become easier to analyze. For instance, problems involving counting configurations, analyzing graphs, or studying distributions can be reformulated using Fourier transforms over finite groups, allowing complex relationships to be handled algebraically. This connection is especially useful in areas like probabilistic combinatorics, coding theory, and additive combinatorics, where frequency based representations reveal hidden regularities and enable efficient problem solving. A few approaches and subfields of combinatorics are enumerative combinatorics. This focuses on counting discrete structures using formulas and generating functions. Fourier transforms help analyze periodicity and derive compact representations of counting sequences. Next, analytic combinatorics. It uses tools from complex analysis and Fourier methods to study asymptotic behavior of combinatorial structures through generating functions and frequency-based approximations. Then, partition theory. It studies ways of decomposing integers into subs. Fourier analysis and Q-series help analyze distribution patterns and asymptotic growth of partitions. The graph theory. This theory examines vertices and edges. Spectral graph theory uses Fourier-like eigenvalue analysis of adjacency matrices to study connectivity, expansion, and structural properties. The design theory. It deals with structured subsets satisfying constraints. Fourier methods help analyze balance, symmetry, and uniformity in combinatorial designs and coding structures. The finite geometry. It studies geometric systems with finite points. Fourier techniques help analyze incidence structures and symmetry properties in discrete geometric configurations. The order theory. This theory explores partially ordered sets. Fourier-like transforms on Boolean lattices help analyze subset relations and combinatorial hierarchies. The matroid theory. It abstracts independent structures. Fourier analysis assists in studying combinatorial invariance and structural properties through algebraic representation. Extremo combinatorics focuses on maximum or minimum structures under constraints. Fourier methods help bound sizes and detect hidden regularities in large combinatorial systems. The Ramsey theory studies unavoidable patterns in large systems. Fourier analysis helps identify structure within randomness and prove existence of ordered substructures. The probabilistic combinatorics uses probability to study combinatorial objects. Fourier transforms analyze distributions, randomness, and expectations in discrete random systems. Algebraic combinatorics combines algebra with combinatorics. Fourier analysis on groups helps study symmetry, representation theory, and combinatorial structures algebraically. Combinatorics on words. It studies sequences and patterns in strings. Fourier techniques analyze periodicity, repetition, and structure in symbolic sequences. Geometric combinatorics. It examines discrete geometric objects. Fourier analysis helps study spatial distributions and structural properties of polytopes and point sets. Topological combinatorics applies topology to combinatorics. Fourier methods help analyze combinatorial structures embedded in continuous spaces. Arithmetic combinatorics studies combinatorial properties of numbers. Fourier analysis is central for understanding additive structures, patterns, and distributions in number sets. Infinitary combinatorics extends combinatorics to infinite sets. Fourier-like tools help analyze structure and behavior in infinite discrete systems. The combinatorial optimization focuses on finding optimal discrete solution. Fourier methods here help analyze cost structures and improve algorithmic efficiency. The coding theory designs error correcting codes. In this, Fourier analysis helps in studying signal properties, detecting errors, and optimizing the encoding decoding processes. The discrete and computational geometry. It studies the geometric algorithms and structures. Fourier transforms assist in analyzing spatial data and optimizing geometric computation. Next application is option pricing. Valuation of options becomes mathematically complex because the option premium depends on multiple interacting factors such as the underlying price, volatility, time to expiry, and interest rates. At its core, the pricing problem is about finding the expected payoff of an option under a risk neutral probability distribution and then discounting it back to the present. Fourier analysis plays a powerful role in this process by transforming the problem from the price domain into the frequency domain, where complex probability distributions and payoff structures often become easier to handle and compute. In traditional models like Black-Scholes, assumptions about the underlying asset's behavior allowed closed form solutions. However, in more realistic settings, such as when volatility is stochastic, as in the Heston model, or when returns are not normally distributed, the probability distribution of the underlying price becomes complicated. Instead of working directly with this distribution, Fourier analysis allows us to work with its characteristic function, which is essentially the Fourier transform of the probability distribution. The advantage is that the probability density function may be difficult to express explicitly. Its characteristic function often has a clean and tractable form. In option valuation, the payoff function is combined with the probability distribution of the underlying asset at maturity. Normally, this would require integrating the payoff against the probability density, which can be computationally expensive or even infeasible for complex models. Fourier methods simplify this by converting the convolution-like operation into a multiplication in the frequency domain. This is where the convolution property of Fourier transforms becomes extremely useful. Instead of directly integrating complicated functions, we transform them, multiply them, and then apply an inverse transform to obtain the option price. A well-known application of this idea is the car maiden approach, where option prices are computed using the fast Fourier transform. In this method, the option pricing problem is reformulated so that the Fourier transform of the option price can be expressed in terms of the characteristic function of the underlying asset's log price. Once this transform representation is obtained, numerical techniques like FFT are used to efficiently compute option prices across a range of strike prices simultaneously. This makes Fourier-based methods particularly attractive in practice, especially for calibrating models to market data and constructing volatility surfaces. Fourier analysis is also closely tied to how volatility and other factors affect option premiums. Since the option price depends on the distribution of future prices, any factor that changes this distribution, such as increased volatility, will alter its frequency representation. Higher volatility spreads out the distribution, which in the frequency domain affects the decay and shape of the characteristic function, ultimately increasing the option's time value component. Similarly, factors like interest rates and dividends influence the drift and scaling of the distribution, which are naturally incorporated into the Fourier-based framework through adjustments in the characteristic function. In more advanced pricing models, such as those used after the financial crisis, Fourier methods remain relevant even when incorporating additional complexities like stochastic volatility, jumps in asset prices, or counterparty risk adjustments (CVA). These models often lack closed form solutions in the time domain, but their characteristic functions can still be derived, making Fourier-based pricing a flexible and robust numerical tool. Combined with risk-neutral valuation, the process typically involves constructing the characteristic function under the chosen model, computing the transformed payoff, and then applying inverse Fourier techniques to recover the option premium. Overall, Fourier analysis enhances option valuation by transforming a difficult integration problem into a more manageable algebraic one in the frequency domain. By working with characteristic functions instead of probability densities, it allows efficient computation of option prices even under complex models, supports fast numerical methods like FFT, and provides a unified framework for incorporating key factors such as volatility, time value, and risk adjustments into the pricing process. Next application is number theory. Number theory is the branch of mathematics that studies integers and their fundamental properties such as divisibility, prime numbers, congruences, and solutions to linear equations. And although these problems are often simple to state, they quickly become deeply complex when we try to understand the patterns like how primes are distributed or how integers behave under modular arithmetic. Traditionally, before the introduction of Fourier analysis, number theory relied heavily on direct, discrete, and often combinatorial or algebraic methods. For example, To study primes, mathematicians used tools like factorization, the Euclidean algorithm, or congruences, and results like Fermat's little theorem. These methods were powerful but limited because they integrated integers as isolated objects, making it extremely difficult to detect large-scale patterns. This is why problems like the distribution of primes remained mysterious for centuries. Historically, this direct approach led to many important but localized results. Euclid proved infinitely many primes. Euler connected primes through product formulas, and Gauss conjectured the prime theorem. But none of these approaches could fully explain how primes are distributed globally across the integers. The breakthrough came when mathematicians began using ideas from analysis, especially Fourier analysis, to transform number theory into what we now call analytic number theory. The key idea is to stop looking at integers purely as discrete objects and instead represent arithmetic functions using oscillatory components, much like how a sound wave is decomposed into frequencies. This transformation converts a hard arithmetic problem into a smoother analytical one, where we can use tools like limits, integrals, and complex functions. A key example is modular arithmetic. Without Fourier analysis, solving congruences involves case-by-case reasoning or algebraic manipulation. With Fourier analysis, we introduce exponential sums which act as filters and vanish unless certain modular conditions are satisfied, allowing us to isolate specific residues efficiently. This is especially useful in detecting periodicity in sequences of integers. Similarly, when studying additive problems, we deal with convolutions of functions. Without Fourier analysis, convolution is computationally heavy, but Fourier transforms simplify it by turning addition into multiplication in the frequency domain, which is far easier to handle. The most profound impact appears in the study of prime numbers. Without Fourier analysis, primes seem irregular and unpredictable. With it, we analyze functions like the Riemann zeta function, which encodes information about primes through Euler's product formula. This function can be studied using techniques closely related to Fourier transforms, where oscillatory terms reveal deep connections between primes and complex exponentials. For instance, the distribution of primes can be approximated using analytic expressions derived from these transforms, something that was impossible with purely elementary methods. In this sense, Fourier analysis converts the chaotic appearance of primes into a structured frequency signal where patterns become visible through their harmonic components. Another important application is in solving partial sums and estimating arithmetic functions. Without Fourier methods, estimating sums requires intricate combinatorial arguments. With Fourier analysis, we express such sums as integrals over exponential functions, smoothing out irregularities and making asymptotic behavior easier to study. Comparing both approaches historically, early number theory was like trying to understand a complex piece of music by examining each note individually. Useful but limited in revealing the overall structure. Fourier analysis, on the other hand, is like identifying the underlying harmonics and frequencies, allowing us to see the global pattern behind the sound. This shift from discrete to analytical thinking transformed number theory in the 19th and 20th centuries, enabling breakthroughs such as the proof of the prime number theorem. and deeper insights into the distribution of primes and arithmetic functions. Fourier analysis is not just an additional tool in number theory, it fundamentally changes how problems are approached by translating discrete integer problems into the language of continuous frequencies and oscillations. It allows mathematicians to uncover hidden structures, simplify complex relationships, and achieve results that are nearly impossible using purely elementary methods, making it indispensable for a deeper understanding of the behavior of numbers. Over to Karthik.
So, guys, as of now, we have understood the mathematical applications of Fourier analysis. Now, let's talk about the uses of Fourier analysis in day to day use applications. First, being the signal processing analysis. Precisely, we do this through a process known as the Fourier transform. What the Fourier transform does is it takes a signal, probably composed of functions of a whole bunch of different frequencies, and take them from the time domain into the frequency domain. That is, it decomposes a signal which is a function of time into the various frequencies that make it up. As you can see in the following image, components that contribute to more of the signal having a higher amplitude of or height are represented as large spikes in the frequency domain. As you can see the few examples of signal being transformed using Fourier transform, as you can see some cosine and sine functions being transmitted as a single frequency or uniform band of frequencies. But we cannot apply the Fourier transform directly in its continuous form when working on a computer, because computers cannot process continuous signals the way we do mathematically on paper. Instead, the signal must first be converted into a discrete form by sampling it at regular intervals, effectively breaking into a finite set of data points. This process allows the continuous signal to be represented in a way that a computer can store and manipulate. Once the signal is disguised, a modified version of the Fourier transform, such as the discrete Fourier transform (DFT) or its efficient implementation, the fast Fourier transform (FFT), is applied. This enables the computer to analyze the frequency components of the signal accurately and efficiently while working with its digital and finite computational framework. To be slightly more precise about what's happening before we apply the Fourier transform, in anticipation of a more rigorous treatment later to come, we can go through some steps. The step one is we take a signal and imagine it is periodic. That is, rewrites its functions such as it represents at some interval. Step 2, our continuous signal is sampled at discrete periods in time. Step 3, we use some numerical methods to approximate these samples and generate a continuous function based on those samples. The next step, we use discrete the continuous function we have fitted so both the time and amplitude are discrete. Step 5, we apply the Fourier transform to move to the frequency domain. Now let's head towards how this could be used in our daily life. As of now, we know that we cannot take a signal, break it up into component functions, and organize them by frequency. But why would you want to do this? Well, the simple fact is it gives us a lot of information about the signal in question. Consider the following image of a human voice saying a word, as you can see in the frequency hertz and time second. We can glean a few things from this image. For one thing, if we start to clean the sounds up somewhat, we would simply remove the small, insignificant frequencies, such as those between 150 to 250, 300 to to 400 and 450 to 500 Hz, since they are likely due to noise, since they spread out over a large range and mark little contribution to the overall signal. We could do a lot of things. We could even remove all the very high frequencies if we, for some reason, had extremely sensitive ears. This is very common application of Fourier transform in signal processing. It's why MP3 files tend to be about one-tenth of the size of the same data on a CD. But more interestingly, what we can make note of and confirm is that there are three major harmonics to this person's voice, corresponding to each of these three peaks. Determining these harmonics would have been extremely difficult in the day before Fourier analysis. The fact that we are able to understand these harmonics better has revolutionized our understanding of certain musical instruments and especially of distortion, like the kind you get from guitar pedals or synthesizers. But wait, there's an issue with all of this. An efficient algorithm for actually performing the discrete Fourier transform is not immediately clear. In fact, for hundreds of years after the discrete Fourier transform was first convinced of, the most efficient algorithm for performing it was of big O n square. With such low efficiency, nobody really attempted to process digital signals, especially back in the day when computers took up entire rooms. It was more efficient to just transmit information over the radio than to even attempt to transmit it digitally. Fourier analysis plays a central role in image processing and compression of it because it changes how an image is represented and understood. Instead of treating an image simply as a grid of pixel values, it reinterprets the image as a combination of underlying patterns or waves. This transformation from the spatial domain to the frequency domain allows us to see not just what the image look like, but how its visual information is distributed in terms of gradual changes and sharp variations. This shift in powerful because it's aligning more closely with how many images are structured and how human perceive them. When we apply the discrete Fourier transform to an image, what we are essentially doing is breaking the image down into its constituent frequency components. For a two-dimensional image, this decomposition is performed systematically, first across rows and then across columns, so that every variation in pixel intensity is expressed in terms of frequency patterns. The result is not an image in the usual sense, but a representation that tells us how much of each type of overall shapes and brightnesses, as well as fast charging patterns that correspond to the edges, textures, and noise. In this frequency representation, an important structure emerges. Low frequency components, which correspond to smooth and gradual changes, tends to cluster towards the center of the transformed image. These components carry the most significant visual information, such as the general layout, large objects, and shading. High frequency components, on the other hand, are found farther away from the center and represent fine details like edges, textures, and small irregularities. While these details contribute to sharpness and realism, they are often less critical for basic visual recognition. This distinction is what makes Fourier analysis so useful. It naturally separates an essential information from less critical detail. To make this transformation practical, especially for large images, the fast Fourier transform FFT is used. The FFT is an efficient algorithm that computes the same result as the DFT, but in a fraction of a time. Without it, working with frequency representations would be computationally expensive and impractical for real world applications like real time image processing or compressing it. Once an image is in the frequency domain, it becomes much easier to manipulate specific aspects of it through filtering. For instance, if an image contains noise, that noise usually appears as high frequency variation. By applying a low pass filter which removes or reduces high frequency components, the noise can be suppressed, resulting in a smoother image. On the other hand, if the goal is to highlight edges or enhance sharpness, a high pass filter can be applied to retain high frequency components while reducing the low frequency background. This makes edges and fine details more prominent. Beyond simple filtering, frequency analysis can also be used to feature extraction, where recurring patterns or directional structures such as horizontal lines and text documents can be identified by analyzing peaks in the frequency domain. The same principles extend naturally to image compression. The key idea behind Fourier based compression is that not all frequency components are equally important. In most natural images, a large portion of the visual information is concentrated in a relatively small number of low frequency components, while many high frequency components have very small magnitudes and contribute less to the precise quality. Compression techniques take advantage of this by selectively preserving the most significant components and discarding or reducing the rest. One of the main steps in this process is thresholding, where only the largest and the most important frequency components are retained, and the smaller ones are set to be zero. In many cases, this means that only a small percentage, sometimes as little as 1 to 5% of the original data needs to be stored. Following this, quantization is applied, where the precision of the remaining coefficient is reduced. Since the human eye is less sensitive to small variation in high frequency details, this reduction is in precision often has little noticeable effect on the image's appearance. The remaining data, now much smaller and more structured, can be stored effectively using encoding techniques. When the image needs to be viewed again, the stored frequency components are transformed back into the spatial domain using the inverse process. This reconstruction does not perfectly reproduce the original image, but it reproduces a close approximation that retains the most information visual features. If the compression has been done carefully, the loss in quality is minimal and often imperceptible to the human eye. This approach offers significant advantages. It enables very high compression ratio, sometimes reducing file size by 100 to 500 times, while still maintaining a visually acceptable image. It is particularly effective for images with smooth gradients and large uniform regions, where most of the information lies in low frequency components. However, it is also has limitations. Imagine with a lot of fine detail such as grass, fur, or complex textures contain more significant high frequency information and are therefore harder to compress without noticeable quality loss. Additionally, aggressive compression can introduce artifacts such as blurring or ringing effects, which appears as distortion near edges. Overall, Fourier analysis provides a fundamental different and more efficient way to handle images by focusing on their underlying frequency content. By decomposing an image into pattern, identifying which pattern matters most and selectively precising them, it becomes possible to perform both image enhancement and compression in a highly effective manner. Coming to the third application is musical tones and repeating waveforms. Musical tones and repeating waveforms can be understood much more deeply when viewed through the lens of Fourier analysis, which produces a synthetic way to represent any complex periodic signal as a sum of simple sinusoidal components. When a musical instrument produces a sustainable note, it generates a periodic waveform in the time domain, meaning the air pressure variation repeats at regular intervals. The rate of this repetition defies the fundamental frequency which determines the perceived pitch of the sound. However, most real world sounds are not pure sinusoidals. Instead, they are complex waveforms composed of the fundamental frequency along with a series of harmonics or overtones. These harmonics occurs at interval multiples of the fundamental frequency and collectively defines the timbre or tone color of the sound. For example, when a guitar string vibrates, it does not only it does so not only as a whole but also in segments, producing multiple frequency components simultaneously, which combine to form a rich and distinctive waveform. Fourier analysis, particularly through the Fourier transform, allows us to move from the time domain representation of this waveform into the frequency domain, where the signal is described in terms of its special components. This transformation decomposes the complex waveform into a set of sinusoidal basic functions, each characteristics by a specified frequency, amplitude, and phase. The resulting frequency spectrum provides a clear visualization of the signal's harmonic structure, showing the fundamental frequency as the dominant spectral peak and the harmonics as additional peak at higher frequencies. For instance, a pure sine wave, such as that produced by a tuning fork, would appear as a single spectral line, whereas a square wave would exhibit a series of odd harmonics with decreasing amplitudes, and a triangle wave would show a similar pattern but with a faster attenuation of higher order components. The concept of spectral decomposition is particularly useful in distinguishing between different sound sources, even when two instruments play the same fundamental frequency. Their spectral envelopes, the distribution of amplitudes across harmonics, differ significantly. A trumpet, for example, typically exhibits strong high frequency harmonics, resulting in a bright and penetrating sound, while a flute has a spectrum dominated by the fundamental with relatively kamzor, highly harmonics, producing a softer, more sinusoidal tone. Similarly, the human voice can be analyzed in terms of its formats, which are frequency bands where energy is concentrated, and these formats shift depends on the shape of the vocal tract, allowing us to distinguish between different vowel sounds. Beyond analysis, Fourier methods also enable synthesis through the principle of superposition, where a complex waveform can be reconstructed by summing its individual sinusoidal components. This is the foundation of additive synthesis in electronic music, where multiple sine waves are combined to create complex tones that mimic real instruments or produce entirely new sounds. For example, a synthesizer can repeat the sound of a bell by carefully selecting and combining frequencies with specific amplitudes and phase relationships, effectively reconstructing the waveform identified through Fourier decomposition. This demonstrates how the inverse Fourier transform allows us to transition back from the frequency domain to the time domain, presenting the essential characteristics of the original signal. Fourier analysis is also central to many practical audio processing applications. In equalization, the signal is transformed into the frequency domain so that the specific frequency bands can be amplified or attenuated, allowing engineers to shape the tonal balance of audio recordings. In noise, in noise reduction, unwanted high frequency components can be selectively filtered out, improving signal clarity in audio compressing techniques such as MP3 and AAC. Fourier based transforms are used to exploit psycho psychochaotic principles, identifying frequency components that are less predictable to the human ear and either reducing their precision or removing them entirely. This results in significant data reduction while maintaining quality. Additionally, phenomena such as missing fundamental highlights how the brain interprets harmonic relationships. Even when the fundamental frequency is absent, the presence of its harmonics allows the auditory system to infer the original pitch, effectively performing a form of spectral analysis. In conclusion, Fourier analysis produces a comprehensive framework for understanding musical tones by transforming complex time domain waveforms into structural frequency domain representation through spectral decomposition. It reveals the fundamental frequency, harmonics, amplitudes, and phase relationships that defines pitch and timbre while also enabling synthesizes, filtering, and comprehension by breaking down sounds into its constituent sinusoidal components and allowing precise manipulation of these elements. Fourier analysis not only explains how musical tones are formed and perceived, but also underpins the technologies used to analyze, recreate, and optimize sounds in modern audio systems. Coming to the last application of Fourier analysis is cryptography. Cryptography is the science of securing communication so that only the intended person can understand the message. At its core, at its core, it works by converting readable data called plain text into an unreadable format called as syntax using an algorithm and a key. Only someone who has the correct key can convert it back through description. Earlier, cryptography was mainly about simple encryptions techniques like substitution and transposition ciphers. But modern cryptography is much more advanced and is deeply connected with mathematics, computer science, and engineering. Today, it ensures not only confidentially but also about data integrity, authentication, and non repudiation, which are essential for applications like online banking, securing messaging, and digital payments. There are basically two types of cryptographic systems. In, in symmetric cryptography, the same key is used for both encryption and decryption, making it fast because difficult to manage securely because the key must be shared safely. In asymmetric cryptography, two keys are used, a public key for encryption and a private key for decryption, which solves the keys sharing problem but is computationally slower. In addition, cryptographic hash functions are used to convert data into a fixed length value that cannot be reversed, making them useful for password storage and digital signatures. On the other hand, is the study of breaking cryptographic systems by finding patterns, weaknesses, or exploiting computational limits. Now, when we bring Fourier analysis to it, the connection between becomes really interesting. Fourier analysis is a mathematical tool that converts data from its normal form, like time or sequence, into a frequency based representation. In simple terms, In simple terms, it helps us see hidden patterns and repetition that are not obvious in the original data. This is extremely useful in cryptography, especially in cryptanalysis, analysis, because many inscription methods, especially older ones, leave behind patterns that can be detected. On the One of the most important use of Fourier analysis in cryptography is detecting predicity. Some classical inscription method like the use repeating keys, while these repetition may not be obvious in the raw text, Fourier analysis can reveal them by transforming the data into the frequency domain, making it easier to identify repeating cycles and thus breaking the cipher. That this is more advanced version of frequency analysis used in the classical cryptanalysis. analysis. Fourier analysis is also important in modern communicational efficiency. Many cryptographic algorithms, especially those based on number theory like RSA, involves operation on a very large number. Techniques derived from the Fourier transforms, such as the fast Fourier transform (FFT), are used to speed up larger integer multiplication and polynomial operation, making encryption and decryption more efficient in real-world systems. Another major application is in side channel attacks, where attackers do not directly break the encryption algorithm, but instead analyze physical signals like power consumption, electromagnetic waves, or timing information from a device. These signals can be transformed using Fourier analysis to identify patterns and extract secret keys. This shows that Fourier analysis is not only useful for building cryptographic systems but also from breaking it down. In advanced and future cryptographic systems, especially post-quantum cryptography, Fourier analysis plays a role in lattice-based methods, which rely on complex mathematical structures. These systems are being developed to resist attacks from the quantum computers, and Fourier techniques helps in analyzing and constructing such secure systems. Coming to the conclusion, Fourier analysis is ultimately about revealing hidden structures inside complex data by changing how we look at it. Instead of viewing signals, images, sounds, or data only in their original form, like time, space, or sequence, it transforms them into a frequency based perspective where patterns, repetitions, and important features became much clearer. In simple terms, it breaks complicated things into simpler building blocks, sine and cosine waves, analyze those components, and then allows us to modify, compress, enhance, or reconstruct the original data efficiently. The key takeaways is that it converts data from the time or spatial domain to frequency domain. It helps identify patterns, noise, and important features. It enables efficient computation via FFT. It is the backbone of signal processing, image compression, audio analysis, wave physics, and even cryptography. Finally, Fourier analysis is a universal mathematical lens that helps us decompose, understand, and manipulate complex real world phenomena by understanding their underlying frequencies, making it one of the most powerful tools connecting mathematics to practical technology. So now let's get into something interesting and let's start with quiz. So guys, you can either scan the QR or go to the website and enter the code, and you can join to the quiz part. Okay, guys, I hope everyone has joined. I'm going to start within 1 minute. Okay, guys, let's start with the quiz. Here we go. Single choice, be careful. Now, going to the second question. Here we go. Guys, the faster you play, the more points you get. So be as quick as possible. What does Fourier analysis help us identify in a signal? Option 1, only amplitude, only time duration, frequencies and their strengths. And the correct answer is frequencies and their strengths. Hope you all get correct. Going towards the next question. What does the principle of superposition state? Signals cannot be combined. Complex waves can be formed by adding simple waves. Only sine waves can exist. Okay. Now you can see the leaderboard. Now let's go towards the next question. Question number 5. In option pricing, what does Fourier analysis mainly simplify? Stock market prediction, complex integration using probability distribution, interest rate calculation only. And the correct answer is complex integration using probability distributions. Now the next question is, which is not a mathematical foundation of Fourier analysis? Thermodynamics, calculus, or linear algebra? Please look that not a mathematical foundation of Fourier analysis mentioned in the speech. Correct answer is thermodynamics. Okay. Hope you all had heard the whole speech. Why is working in the frequency domain useful? It makes signal larger. It simplifies tasks like noise removal and compression. It removes the need for mathematics. Coming to the halfway mark, this is our eighth question, and here it is. What is the key difference between the Fourier series and the Fourier transform? Fourier series use only cosine waves. It simplifies tasks like noise removal and compression. There is no difference. And the correct answer is it simplifies tasks like noise removal and compression. Towards the ninth question is in cryptography, how does Fourier analysis help in breaking certain ciphers? By encrypting data faster, by detecting hidden repeating patterns in data, by generating keys automatically. Correct answer is by detecting hidden repeating patterns in data. Leaderboard after the two-third of the journey. Here we go. Okay, let's go. Why is the discrete DFT importance in real-world applications? It works with discrete and finite data, making it suitable for computers. It eliminates noise automatically. It works only for infinite signals. Now to the next question. What is the main advantage of the FFT? It increases signal accuracy. It converts signals into the time domain. It computes the DFT much faster and more efficiently. In real-world applications, Fourier analysis is widely used for increasing signal speed, signal analysis, solving equation and data compression, only solving algebraic equations. And the answer the signal analysis is solving equation and data compression. To the 13th question is why is Fourier analysis useful in combinatorics? It removes the need of counting. It helps analyze patterns and structures using frequency method. It only applies to geometry. It helps analyze patterns and structures using frequency methods. Okay, guys, you have to be more precise, man. Three questions remains. In signal processing, why do we convert a signal into the frequency domain? To increase signal speed, to identify frequency and remove noise, to make signal continuous. The right answer is to identify frequency and remove noise. The leaderboard. Guys, only two questions remains and both of them are true and false. So be quick. Let's go. Damn, you guys are fast. But the answer is false. To the next question. The Fourier transform can directly be applied to real world digital signals without any pre-processing. Okay. Okay. And then these are the leaderboard. Jay being the first person and the winner of today's quiz. Guys, do comment down your experience and see you next time. Till then, good night. Thank you all for listening, and you can now leave the event. Thank you.
Guys, the Google form for the attendance is in the chat. You can fill the form and leave.